Now let's take a look at some of the different scheduling policies that an operating system could use. So the first one we're going to look at is called first in, first out, or FIFO for short, right? So again, the idea is that there are three processes, P1 and P2 and P3, right? And the idea is that what we're going to do is we are going to actually, now that P1 has arrived first, and this is basically the arrival order, and P1 has arrived first, and if processes are arriving at the same time, we have some way of breaking ties. So for example, we use process IDs to break ties. So it's arrival order or the process with the lowest ID, let's say. So in this context, what would happen is that on your processor, you would actually run P1 first, and then once P1 has completed, then you would run P2, and then when P2 has completed, then you would run P3. It's a very simple scheduling policy. You simply order your process by arrival time and by process ID perhaps, and then you take them and then you run them on the processor. It's very, very simple policy, right? Now, this policy can run into some bad results in certain cases. For example, let's say we had a case where P1 was a really long process, right? It's going to execute for 100 seconds. And then you have P2, which is going to execute for 2 seconds, then P3, which is going to execute for another 2 seconds, right? So under FIFO, because P1 came first, you're actually going to be running P1 for 100 seconds before you actually get to P2 or to P3. Right? So this is really bad for turnaround time and response time. So if P2 is a terminal job, like you're typing something in your terminal, you don't want to wait 100 seconds for some other process to actually complete before you get to see what files you have in your directory or something, right? So FIFO is very good in the sense that it's very simple, and simple policies have fewer bugs. But it's also not great for turnaround time and responsiveness. And also, overall, it's not a policy that's sort of widely deployed for that reason. So, given that FIFO has this sort of critical flaw, what can we do? In this same situation, if we wanted to optimize for, let's say, responsiveness, one thing we could do is we could employ a policy called it's called shortest job first. Or SJF for short, right? So in this context, what we're going to do is we're basically going to say we're going to look at all the processes that have arrived, and whatever is the shortest, we're going to run that the first. So for example, we're going to take P2, which is P2 and P3 are both going to run for 2 seconds. So we're going to take P2, we're going to run P2. After that, we're going to run P3, and finally, we're going to run P1. So this is the order in which shortest job first would execute. Shortest job first is actually extremely good for turnaround time and responsiveness, right? Because you're always picking the shortest job first. So jobs which need response from the where the user is expecting a response typically tend to be short-lived tasks, right? All it really does is it's sending a message to the operating system, or the operating system is sending out a message to the user. So those tend to be scheduled first in shortest job first, and then finally you're executing your process P1. Now, one thing to note is that in both first in, first out and in shortest job first, the total amount of time taken is going to be the same, right? Because the total amount of time taken is just the sum of the running times of all the three processes that are there. So the total size of this bar is going to be the same. But because we are executing the shortest jobs first, the responsiveness to the user is going to be much better. So that's shortest job first. The problem with the shortest job first is that it really is dependent upon the arrival time of your processes, right? So in this particular example, we assume that everything arrived at the same time. However, imagine a scenario where this arrived at second 1, this arrived at second 5, and then this arrived at second 7, right? Now, remember that we don't stop anything once it starts running, right? So because of that, the situation is going to be shortest job first looks at everything that's arrived at time 1. There's only one thing that has arrived at time 1, which is P1. So then it's going to start executing P1, right? And then it's going to execute that for 100 seconds because it doesn't stop anything. So for 100 seconds, P1 is going to execute, and only at that end point is it just going to say, oh, like I'm done, like what do I execute next? So then it would see that like P2 and P3 have arrived and it's going to execute one of them. But that's like no help to anybody. In fact, it's pretty much going to be the same as first in, first out. So this is sort of like the big problem with the shortest job first. It's really dependent upon the arrival time of the different processes. So if the arrival time is slightly skewed such that the longer processes come first, it's going to behave pretty much the same as first in, first out, where the longer processes may be executing for like a really long period of time, right? So there is a variant of this that avoids this problem, and it does something called preemption. So the idea of preemption is that you are executing a process and then you're going to say it's not fully done. Like the process, for example, let's say is going to execute, it needs to execute for 10 seconds. That's horrible. It needs to execute for let's say 10 seconds, but I'm going to execute it for let's say 2 seconds and then I'm going to stop it. And I'm going to stop it, I'm going to do something else, and then maybe I'll come back and then execute it for another 3 seconds and so on until the job is finished. So preemption is this really important feature of scheduling algorithms. What it means is that even if you start running something, you are not stuck with running that until the job ends. So even though you may be running a really long task, if you see that there are other tasks that are waiting which are like shorter and need a user response, you can stop this task and you can go and run this other task. So to do preemption, the sort of like important hardware thing that's required is that you should be able to do a context switch, right? So as we just saw, when you're doing a preemption, you're stopping the process in the middle of like whatever it is it was doing, then you're going to say, I'm going to run you again at some later point of time. The mechanism that is required for doing this is the context switch, being able to save the state of a process and then restore that state and then continue running, right? So if we look at the scheduling policies, you can clearly separate out like preemptive scheduling policies and non-preemptive scheduling policies. So FIFO and shortest job first were non-preemptive scheduling policies. Let's look at one that is preemptive. So this is called shortest time to completion, basically. Shortest job time to completion, or SJCF for short. First. So the idea is that we are taking shortest job first. Instead of saying it looks at the total size of the job, we're going to look at like how much of the job is left, right? So let's sort of like look at an example of this, and we're going to go back to our previous example of this 100 thing, right? So we have process P1, which is going to run for 100 seconds. Then we have process P2, which is going to run for let's say 2 seconds. And then we have process P3, which is going to run for 3 seconds, let's say, right? And let's say this arrives at time 1, and then this arrives at time, say 5, and then this arrives at time 7, okay? Initially at time 1, which is the first time point at which there's anything to be done, shortest job time to completion will look at this and will say, oh, like there's only one job, let me start running P1, right? So it starts at time 1, okay? Now at time 5, it looks at the jobs that are currently there, which is P1. So P1 at this point of time will still have 96 seconds, and then P2, which has just arrived, will have 2 seconds. So the right thing to do is to run P2, or according to this policy, the right thing to do is to run P2, right? So from time 6 to, let's say, 7, or let's say 8, say 8, P2 is going to run, right? Now at this point of time, it's going to once again look at like what's left. So P2 has completed, P1 still has 96, and then there is P3, which has 3 seconds left. Okay, so now the right thing to do is to run P3. Let's say it runs from 9 to 12, and then it's going to run P1 all the way until it finishes. So that's the way that the SJCF is going to execute. One sort of like slight nuance here is that at time 7, like in the middle of P2 executing, process P3 arrives. So instead of looking at this point when at 8, it is actually going to look at time 7, but then there will be 1 second left of P2 and then 3 seconds in P3, so it's not going to do anything at this point. It's going to finish off P2, then it's going to run P3 and then run P1. So this scheduling algorithm is actually optimal under the assumptions that we have made. So if you're always going to be running the job that is the shortest time to completion, what you're ensuring is that the total time taken is going to be the same, but you get very good response and turnaround time. So this is sort of like an optimal algorithm. The problem with this algorithm is that it assumes that we know how long a task wants to run. So for example, P1 saying it wants to run for 100 seconds, that actually never happens in real life. The processes never tell you like how much time they want to run. Every process is just going to say, give me some time, right? And then we have to estimate like, oh, maybe this process will run for 5 seconds. This is a process that looks like it's a terminal. It's going to run for like a short amount of time and so on. So there are other details that we'll get into the next class, but we try to estimate whether this is a batch process, it's going to run for a really long time, or it's going to be an interactive process which is going to run for a really short time, and we schedule based on that. So this is how shortest job to completion first works. And one other sort of like algorithm to sort of round all of this out is called round robin. And the idea there is very, very simple. So it's still a preemptive algorithm. So you're still going to be stopping your process, but the way it's going to work is you're basically going to give every process some amount of time. So for example, you could give 2 seconds to every process. So P1 is going to run for 2 seconds, and then it's actually going to run twice, because like until second 5, the second process doesn't arrive. So from time 1 to time 3, P1 is going to run. Then from, let's say, time 4 to time 6, P1 is going to run. Now P2 has arrived, so P2 is going to run from, let's say, 7 to 9. And then at this later point of time, again P1 is going to run, but only for 2 seconds. So you see how it goes. You alternate between every process that is available for running. And the really good thing about round robin is that it's very fair, right? It doesn't matter if it's a batch process or an interactive process or whatever. It's going to give you a small amount of time to all your processes, and interactive processes are going to get done sooner, right? So that's really the benefit of it. It's a very fair thing. Response time is not great though, because like you can imagine there is 100 interactive processes waiting, and there's 100 long-running processes waiting, and round robin is going to just like go through one of them at a time. It can take a lot of time until it schedules the interactive process. So it's not great for response time, but it is very good in the sense for like a fairness. And it's a very simple algorithm, less liable to mistakes. So you see that there's a bunch of like different scheduling policies, and in real life, like in operating systems like Linux and Windows, they use complex variants of this. But these are sort of like the basics that you should know if you want to actually go look at different operating systems.